Okay, this is the term 2, week 8 Physics CA. Before starting, I want to shout out Taim Sakhnini, Ryan Abdullah, and Hamza Tayloni. Uh, yeah, yeah, that's it. Let me start this week. The moments where you have to learn the rule sigma m equals 0. Okay, what are you saying, Walid? You'll understand. Don't worry. Um, State the conditions for equilibrium. Uh, Look, it's all about the turning effect. Remember, we had moments. Now we're looking at two moments uh, that are together across a certain plank. You'd say you have a plank like this, and you have a force acting like this, let's say 10, and a force here 20. Okay, and you want to put it. You need to position the turning the they call it the fulcrum. You want to know where to put this fulcrum. The fulcrum is yani the center of it. It doesn't have to be in the middle. Sometimes it can be here, sometimes it can be here. But you have to know that the closer you move it to the right is because uh sorry, what? Yeah, my fault. It always moves, the fulcrum always moves towards the heavier side. Because yani, for example, when you hang a painting, let's say this is my painting, yeah? It's over here. It's like a person. Okay, you want to hang it. Usually you put it in the middle to balance out both sides because both masses are equal. But sometimes, you would see a tilted painting. Sometimes you would see a painting hung on the wall that's kind of bent. So it kind of looks like this. Same painting, same person, like this. But it's like this. Why? Because you'd see uh, it like to fix it, to make it straight, you would obviously push it back and make it, yeah, hang it in the middle. This happens when you hang it like from the side, if you know what I mean. What I'm trying to say is if you hang something not in the center of gravity, then it's going to be tilted. For our whole goal of this experiment here for the 1020, we want to find the center of gravity, not center of gravity, but let's say we want to find the center of moments to make it that the moments will cancel out and it stays even. It doesn't bend, it doesn't move left or right. So obviously here, if both masses are equal, it's going to be in the middle. Uh, and if you move it to the left, the painting is going to hang like that. So that's why in question 4, when they say that this lamina was suspended from point A, it's hung like this. It started hanging, but from point A, and point A isn't at the middle. What's gonna happen? Obviously, it's gonna be tilted towards the left, right? So instead of like this, it's gonna be tilted with the left side hanging up, like this now. A will be like this, B will be over here. Actually, more, it should be more. It should be like this. A is over here, B was over here, C is over here, and E is over here. So what they're asking in part A is which one's going to be vertical. Obviously, it's going to be AB. Why now is this vertical? Because we tilted it to the left. Okay, that's it. And then they say that the weight of lamina, they want the weight of the lamina about A as it hangs freely. Okay, they want the moment of it. Okay, look. Obviously now, once it's hanging like this, and you have A, right? And you have the weight which goes straight down, right? They want the moment of this weight. I think all of you know why it's zero. Uh, it's zero because it's passing through A. Remember, if you had anything passing through the fulcrum or your point of rotation, the moment of it will be zero. So I skipped the first three. Let me do them fast. So for a body to be at equilibrium, like here, where yani both sides are equal, the the net force, so sigma F is zero and sigma M is zero. Okay, sigma F equals zero gets you translational equilibrium. In case they ask this, translational equilibrium, and sigma M gets you rotational equilibrium. Okay, so to have any object to be at equilibrium, the net force should be 0 and the net moment should be 0. Okay, here. Question 2. The moment in which an object has a constant speed in one direction is URM. Everybody knows this. And which one it uh, increases velocity by equal amounts is uniformly accelerated. Everybody knows this. 4, we did it. Let's move to 5. Calculate the moment of a couple. Everybody knows this now. The moment of any couple is actually equal to force times the distance between it. So the moment of this couple is 15 times the distance between it, which is 2 centimeters, which is 0.02 meters. So 15 times 0.02, which is 0.3. Question 6. Uh, okay, have a look here. Two downward forces of respective magnitudes 50 and x newtons, drawn here, are applied to a uniform plank of weight 20 newtons. The center of the plank is placed on the fulcrum and the forces are applied respectively 25 centimeters and 50 centimeters from the fulcrum. Okay, they want the magnitude of x. Okay, you want to look here. They said that the plank is in equilibrium. Okay, so that means the sigma m should be equal to 0. This is how I solve. This is how my teacher taught me to solve. Sigma m is equal to 0. Okay, what does this mean? That the moment 1 plus moment 2 plus moment 3 plus moment infinity is going to be 0. In this case, if you want to solve to find the magnitude of x, know that sigma m is 0 because it's equilibrium. Okay, if you want to solve any equilibrium questions, I have a few steps that I like to put in before solving. The first thing I like doing is know all of the forces you have. Okay, know all of the forces you have. You have a lamina over here, okay, and you know that the weight of the plank, other than this 50 and this x, is obviously 20 newtons. There's always a weight, always 20 newtons acting downwards. Okay, and this 20 newtons is cancelled out by the normal force, which is 20 also. Okay, but these cancel out, so there's no reason to write it now. Okay, the second thing I like to do is find your point of rotation. Always set a point of rotation. In this case, it's already given, it's over here. Okay, if it's already given, you can skip that part. The second case is apply sigma m equal, the last step is to apply sigma m equals 0. Let's apply. What's the moment of 50 around this fulcrum over here? It's actually 50 force times the distance. It's the moment is equal to plus minus the force times the distance perpendicular. Okay, and the moment is equal, in this case, it's counterclockwise, right? And it's obvious, I don't think I have to draw it. It's counterclockwise, so plus the force 50 times the perpendicular, so times the distance 25. Okay, let's call this moment A. How about moment B? It's going to be x minus x, sorry, because it's just obviously clockwise, minus x times the distance, which is 40. So 50 times 25 minus 40x equals 0. Let's solve this. 50 times 25 is, I'll do it in front of you. 50 times 25, okay, whoa, 50 times 25, 1250 minus 40x equals 0. Take 40x to the other side, you get 40x equals 1250. So x equals, I think it should be 31.2 on your calculator, divided by 40, 31.2, and they put the answer just 31. Okay, 31.25, and they rounded it to 31. Okay, let's see here now. The upward force exerted by the fulcrum on the plank is how much? Okay, now we have 50 here, we have 31 here. Don't forget you always have the weight, which is 20. In this case, it's 20 newtons. So what will the upward force be? It's going to be the reaction of the fulcrum pushing up all these forces. And how much will that be? 101 newtons. Okay, I know I said that the normal was 20, but as well as the normal, there's also the reaction of these 31 and 50. So there's going to be a 101 Newton push as a reaction. Question 7. Okay, again, same thing. You have a 60 kilogram man on the left, which is sitting 0.8 meters away. His friend of mass 40 kilograms is balancing by the beam by sitting at a distance x from the pivot. Drag and drop from the below the value of x. Okay, again, we have the distances already. Okay, so well, we don't have both, but you have one of them, so there's no need to locate your point of rotation and make one by yourself. uh and what did I say was the other one? And we're not really asked for any forces other than just the distance, so we don't need to locate all the forces that are acting on the plank. In this case, we just have to know that since we're at equilibrium, sigma m equals 0. Let's apply it. What's the first moment? Okay, around here, huh? It's gonna obviously be counterclockwise, so positive 60. Oh, look, if you use 60, you'll get the right answer. But in this case, if you in a written part you say that the force is equal to 60 newtons, you're gonna get it wrong, because the force in this case is the weight of the man, and that weight is equal to the mass times gravity, which is equal to 60 times 10, which is 600. Okay, so anytime you have any masses, always multiplied by 10. Okay, if it's not a force and it's a mass, multiplied by 10. So 600 times the distance 0.8 minus, we have 40 and it's clockwise, so minus, that's why I put minus 40, which turns into 400, because kilograms to newtons, you need to multiply by 10, because W equals mg. Always multiply by 10. If you have kilograms and you want to convert it to a force, you have to multiply by 10, because you know the moment is equal to FD perpendicular. FD, we didn't say the mass times D, we said F. To convert a mass to a weight, you need to multiply by G, which in most cases is 10. But if you use 60 and 40, it works. But I'm just saying for your exams. 60 times 0.8 minus 400 times the distance x, right? Equals 0. Let's do it. 600 times 0.8 is 6 times 0, 6 times 48. I think 4.8. 480 minus 400x equals 0. You get 400x equals 480. X equals 48 over 40, which is 1.2. Question 8. Which one's unstable equilibrium? Okay, انت يعني بيني وبينك. If you leave this uh this cone, let's say cone, if you leave it on this plank over here, don't you think it's gonna fall? يعني I think it's obvious, right? And this one here also, don't you think it's gonna fall or tilt? This one has a stable base, and this one, if you move the ball to the left or to the right, it's gonna end up rolling back down. I think يعني everybody knows this. The ones where it returns to its original shape are stable. The ones where it doesn't are not stable. Question 9. Okay, يعني and you guys know Snell's law is Ni sine I equals Nr sine R. Okay, yeah, I think everybody knows it. Ni is the index of refraction of the incident ray. Since we're going from glass to air, the Ni is the glass, which is 1.6. Sine I is sine 30, because they said incidence is 30. Nr is 1 times sine R. We don't know it, we're trying to find it. 1.6 times sine 30 is 0.8 equals 1 sine R. Obviously, to find R, you have to do shift sine of 0.8, which is 53 after rounding. And I don't have my calculator beside me, but you should get 53. And the ratio of the sine of the angle of incidence to the ratio of that of the angle of refraction is a constant. This is known as the second law of refraction. Memorize it. Question 10. Which one are true? Is this lens being used by a magnifying glass? This was case 1 of the cases, if you guys remember. This lens is being used by a magnifying glass, because case 1, whenever you have virtual, is always magnifying glass. The image is virtual and upright, because it's virtual, because it's these dotted lines that create an image. The actual lines don't create an image. You have to trace it backwards, that's why it's virtual, and obviously it's upright, and it's obvious. The image can only be seen by IQ. Yeah, it can only be seen by IQ because the real rays are popping out from over here. The virtual rays are, you can't see them obviously. You can only see the real rays, and the real rays can only be seen by Q. Question 11. Okay, this is the one where you need to actually apply the rules to solve an equilibrium question. You you have 30 newtons, 20 newtons, and it's a meter stick. A meter stick meaning it's all 1 meter. Okay. In order to balance the stick, and we want to make it equilibrium, we want to know where do we put the upward force, or where do we set the fulcrum. Okay. They want to know where we should put the upward force. The first thing I tell you is أول شيء locate all the forces. Okay, we always have a weight, but in this case it's negligible. Okay, they say that on purpose, so you don't write the weight. What do you think is going to be the reaction to the 30 and 20? It's obviously going to be a 50 Newton reaction, right? So we want this upward force, which is 50 newtons. We want to know where do we place it. It's at a distance of something meters, which obviously is 0.4, from the 30 Newton object. Okay. The second step after locating all your forces, which is 50 newtons, is you have to set a point of moment or set an axis of rotation. Okay. Usually you can set it here. It's called that point A, or you could set it at point B. Solving using both points will be correct. But if you want the straightforward answer, use the point at which they told you the distance from that. If they're telling you from the 30 Newton object, so use the 30 Newton object as your point of moment. But look, here's the thing. In the written part, sometimes they don't tell you from which object, so you can take any point and give any distance, you'll be correct. Let me show you how to solve. Around, let's call this point A, we know that the sigma m around A, it should be equal to 0. We have 3 moments here. Let's call this F1, F2, F3. The moment of F1 is equal to 0. Why do you think? Because look at F1, it intersects with A, so it's 0. The moment of F2, around A obviously, is equal to, look at it, it's actually counterclockwise. It's counterclockwise, so plus 50 times, let's call this distance L. Okay, let's call this distance L. This is how you solve. You want to call it X, you want to call it L, you want to call it Y, I don't care. But you need to put, we don't know the distances, so I'm going to keep it as L. How about the moment of F3 times A? The moment of F3 around A, sorry, is equal to, over here, huh, this is F3, it's equal to minus 20 times 1. Okay, why'd you put 1? Which we don't know the distance? Okay, buddy. This is a meter stick. Meter stick meaning that the meter, this is all 1 meter. This is all 1 meter. That's what it means. And you know the distance from 20 to A is the whole stick, so it's 1 meter. That's it. But this small L is what we don't know. So we know the moments of all of them now, and we know that the sigma m around A should be equal to 0. So that means 0 plus 50L minus 20, because minus 20 times 1 is minus 20, is equal to 0. So 50L equals 20 because you took 20 to the other side. So L equals 2 over 5. So L equals 0.4 meters. If you solve using B as your point of moment, you're going to get 0.6. And that 0.6 will be away from B. So that's why I'm telling you use A, because it will give you the direct answer, 0.4. And to get that direct answer, take 30 newtons as your point of rotation, as your point of rotation. Question 12. A uniform lamina is suspended from point A and a vertical line is drawn through A. Then a lamina is suspended from point B and another vertical line is drawn through B. What is O? O is the center of gravity. Why do we do this? Sometimes for every object you have a center of gravity. Okay, for every object you have a center of gravity. That center of gravity is usually at the center of masses. For example, in a rectangle, the center of gravity would always be at the intersection of the diagonals. Obviously, I drew this wrong, but I'm just trying to get you to learn the idea. In a triangle, it would also be at the intersection of a diagonals. So, oh, okay, whatever. But it's always going to be at the middle, you know? In a square also, it will be at the intersection of the diagonals over here. Okay, that's what the center of gravity is. It's usually at the center. But what if you don't have a regular shape like this paper? To understand this concept, uh, think about the center of gravity being in the middle of the object. But if you have an object like this, you can't just take the point in the middle and say that's the center of gravity. You need to do an experiment. The experiment is done like this. You have a piece of paper, okay? This piece of paper. Obviously it's not a straight rectangle. Let's do like this. I want this piece of paper. I want to find the center of gravity. I'll make it a bit wider. I don't know why I drew it like this. Like this. I want to find the center of gravity of this because this is actually an experiment that's in the book, I think. Center of gravity. The way you do it, you hang it from one edge. So let's hang it from the top of here. After I hang it from the top, I draw a line from that to the other corner. And it's going to look like this. And then what do? I hang it again. This time I'm going to hang it from the right. And if I hang it from the right, you know that obviously it's going to look like this now. Because I'm hanging it from the right. And from the right again, I draw a point. I draw a line. And this line over here was the green line, right? So it's going to be like this. The center of gravity will always be the intersection of the two lines. Okay? That's why O here will be the center of gravity. Thank you so much for watching. Good luck.